In part 1, we described the BMS as the brain and safety controller of a battery pack. Now let's follow what it actually does, from the cell all the way to the sources and loads the pack is connected to. The process can be broken into 4 jobs: measure, estimate, decide, and act. First, the BMS builds a live picture of the pack. Precision cell monitoring electronics measure the voltage of every series cell group. In a small battery, that may all happen on one circuit board. In a large EV or storage pack, monitoring boards usually sit close to the modules and report back to a central controller over an isolated communications link. The BMS cares about more than total pack voltage. It watches the highest cell, the lowest cell, the difference between them, and how quickly these voltages are moving. The total voltage can look normal while one cell is already too low or too high. Thermistors measure temperature at selected points around the cells, bus bars, cooling plates, and in some cases contactors. A current sensor, usually a shunt or a Hall effect device, measures the current that's flowing into and out of the pack at all times. High voltage systems may also monitor the pack voltage, insulation resistance to chassis, and voltage on both sides of the contactors. Raw measurements are only the starting point. The controller also must filter noise, check whether sensor readings are plausible, and compare the data with limits defined for the cell chemistry used in the application. Good protection logic doesn't usually trip from just one noisy sample. It uses warning thresholds, fault delays, and a buffer. A brief current spike may be acceptable, while the same current sustained for several seconds might require a shutdown. The BMS also estimates state of charge, like we discussed last episode. The main tool is Coulomb counting, integrating current over time to track how much charge has entered or left the battery. Because small sensor errors accumulate, the estimate is periodically corrected using known voltage conditions or other reference points. From the same data, the BMS calculates how much charge and discharge current the pack can safely accept right now. Those limits can change continuously with cell voltage, temperature, state of charge, and pack health, or state of health. Once the BMS decides what the battery can safely do, it has to go and then control the system. In a high-power battery pack, the BMS usually operates external contactors rather than carrying the full battery current through its own circuit board. If the setup calls for it, the BMS may operate a precharge sequence before closing the main positive contactor. Precharge uses a second contactor with an inline resistor to slowly charge the capacitors inside a downstream inverter or charger, limiting the initial inrush current, which can damage or weld contactors. The BMS checks that the downstream voltage rises as expected before completing the connection. During operation, the BMS may command the charger or inverter to reduce current instead of immediately opening the contactors. As the highest cell approaches its upper limit, the BMS can taper charge current. If the lowest cell is running out of juice, it can reduce discharge current. Additional factors like temperature and user set points also contribute to these limits. Additionally, the BMS may control pumps, fans, heaters, warning outputs, and interlocks in some setups. A hard shutdown is the last line of control, used when continuing to operate would be unsafe or when another device ignores the BMS limits. Most larger systems communicate over a 2-wire electrical signaling protocol called Controller Area Network, or CAN. The BMS sends state of charge, temperatures, faults, and allowable charge and discharge limits to the rest of the system. Just as important, devices should have timeout behavior. So if valid BMS messages disappear from that CAN communication stack, the charger or inverter needs to move to a safe state. The BMS also balances the cells. Most systems use what's called passive balancing, which places a small bleed resistor across the highest cells to remove a little energy near the top of charge. It's useful for correcting gradual drift, but it's not a repair tool for a weak or badly mismatched cell within the pack. Balancing current is tiny compared with traction or charging current, so the process takes time. So, to recap, a BMS is continuously measuring the pack, estimating its condition, calculating safe limits, and controlling the hardware around it. In part 3, we'll look at the specific failure modes these functions are designed to prevent, and the additional protections that still need to exist outside of the BMS.